Let's try to understand what do you mean by dynamic lift. Before that, we understand that when a body is in a static fluid, it experiences a upthrust, and that upthrust is called beyond force. So, if you look at the beyond force, it's an uplift, upthrust experienced by a fluid that is at rest. That fluid is in the state of rest. Then it is experiencing an upthrust. Here we are extending a concept further. What if the fluid is in the state of motion? So, if fluid is in motion, or there is a relative motion between the fluid and the body, then it experiences there is an upthrust. That upthrust we call here as dynamic lift. That's what we are going to understand now. Of course, if it has happened due to that of the air, we can call it as an aerodynamic lift. We want to understand that how does that's going to happen. Well, let's try to understand it in three different cases. We want to talk about a case where there is a relative motion. So let us consider a case one as, let me consider a case one as when body in the fluid has only translatory motion. Let's talk with a simple case. Translatory motion means all particles of a body. Say this is the ball. This is having a translatory motion means it is moving like this, the velocity v. There's a fluid all around it. So while this is moving, that will influence the fluid. So the fluid that is near to the ball is also experiencing a velocity due to the translatory motion in the same direction of the ball itself. I'm calling it as velocity due to the translatory motion, Vt. Anyway, you can notice the upward and the lower parts of the fluid are equally influenced, and hence they don't have anything like a special dynamic effect. Let us consider a case when the body has only spin motion. It has no translatory motion, but it has only spin motion. What happens in that case to the surrounding fluid is the point that I would like to understand now. So let us consider the same ball, but this time it is spinning like this, say in a clockwise direction. So it is obvious that the fluid around it also moves in a clockwise direction. Like the spinning of the earth is making the spinning of the environment of the earth around it in this way. Thus, this spin gives a velocity to the fluid around it. But if you notice the direction carefully, in the upper portion, direction is in one direction, whereas in the lower portion, the spin direction is in the opposite direction. It's equal influence, but in the opposite directions. But this is a simple case of having only spin. But in real life, like a cricket ball, frisbee, whatever you can see, they will have both these motions, like a translatory motion and a spin motion. Even a fast bowler, when he bowls, the ball turns around. So there is a horizontal motion as well as there is a spin motion. Let us consider that case and try to understand what happens in that case, right? So let's go for the real life case. Case 3. When body has both translatory as well as the spin motion. So like the first case, due to the translatory motion, it will get a velocity Vt both in upper and lower parts. Like the second case, it get a V spin, but in the opposite directions of as it is being shown here. So when the body is having a spin as well as a horizontal motion, translatory motion, you can see the upper parts. See this upper part. It has Vt because of translatory motion. It has Vs because of spin motion. So Vt as well as see the spin motion in this direction, in the same direction, the upper part. Whereas in the lower part, Vt is like this, but V spin is in opposite direction. So if you observe little more carefully, what you can notice is here translator and spin motion are in the same direction. They will add up so that the whole velocity together will be more in the upper part when compared with the lower part, because in the lower part both velocities are in the opposite direction, so the effective velocity will be less. So what you can notice little carefully, what you can observe is in the upper part of that body there is more velocity. More velocity means more kinetic energy. In the lower part less velocity and hence less kinetic energy. There is no significant height difference. Almost both the parts are having the same height, and hence both upper part and lower parts potential energy is not variable, it is same. There's a concept called conservation of energy, which says Bernoulli's theorem says, which says that the potential energy, kinetic energy, and pressure energy per unit mass is constant. Out of that, this potential energy is constant. In the upper part, kinetic energy is more. As their total sum is constant, when one energy increases, it's obvious that the other energy has to decrease. So as the kinetic energy is more, here at this part, pressure energy is less. Here at this part, as the kinetic energy is less, pressure energy is more. So what we can understood basing on the Bernoulli's theorem is, in the upper part there is less pressure energy, whereas in the lower part there is more pressure energy. So upper part pressure energy will try to put it down, whereas lower part pressure energy try to push it up. But what we have understood is lower part has more pressure energy than the upper part. That means there is more force acting from bottom to top when compared with the top to bottom. Thus, the particles experience, the bodies experience a resultant upward force. This is due to the relative motion of the fluid and body. This upward force, resultant upward force experienced by the body is called dynamic lift. This is what do you mean by a simple dynamic lift is. You can see one or two simple applications of this dynamic lift in our real life too. But anyway, I will discuss that in the next video, not to say lose the focus. Right. Thank you. Thank you for watching.